Okay, so here we want to illustrate how, in general, for any problem, no matter what the electric field is, no matter what the charge distribution is, how to get the potential difference between 2 points that are far away. And we're going to just do it by an intuitive way, and then we'll explain the exact way later. So to do that, you need to choose some path between the 2 points. You need to make some kind of path in 3 dimensions. Any path. And we know how to, let's cut up the path into, in this case, 1, 2, 3, 4 parts. Of course, remember, you have to do it an infinite number of parts. I'm just doing it here 4 parts to illustrate the idea. So we know how to get the potential difference between point C1 and point C2. If you know the electric field at point C1, and you know the displacement vector between here and here, delta R1, then the potential at C1 minus the potential at C2 is just the dot product. We know this. We know this is true when delta R is very small, it's infinitesimal. So that's why we put here approximate, because we chose a large distance. This is just for this illustration. So if you want this to become exact, you just need to cut up this path into an infinite number of parts. Then it will become exact. So I'm just doing this file so to illustrate the idea. And then you can go to get C2 minus C3, knowing the electric field at 2 and the displacement vector. Again, it's a dot product. And then you can get the potential at C3 minus C4, which is again the dot product, knowing the electric field at C3. And then you can do the same thing to get C4 minus C5, knowing the electric field at 4. So if you know the electric field at the different points in space, you can get the potential difference between the 2 neighboring points on that path. Now, if you look at the sum, if you add all these terms, what would you get? You see here you have VC2 minus VC2, VC3 minus VC3, VC4 minus VC4. So you end up with the potential at point A, the initial point, minus the potential at point B, the final point. So by adding the potential differences between all these points, when you obtain them in this particular order, you end up with the potential difference between the far point and the far point. So this gives the idea how to get the potential difference between 2 very far points. You add, you cut up, you make a path, and then you get the potential difference between neighboring points and you add them. So adding, and we said you'd have to take the limit when the distance between the 2 points goes to 0, or you have infinite number of parts on this path, then you're doing an integration. So that would give you the exact value. So here I'm just illustrating the idea by cutting it up into 4 parts. So if you want to do it exact, as I mentioned, you would have to take this distance between the 2 points, all the points on this path. You have to cut up the path into an infinite number of parts. So you let delta R go to 0. So you're summing the dot product when the size of each element goes to 0, or the number of elements goes to infinity. That will give you exactly the potential difference between the 2 points. And the limit of sums can be written as an integral. So this limit of sums, you can write it as integration from a to b e dot dr. So you see that when you write down integration of e dot dr from a to b, it contains in it so much information. This integration, what it's doing is, first of all, you have to choose a path. Then you cut up the path into an infinite number of parts. You get this dot product for each part, and then you add over the whole path. You'll end up with the potential at A minus the potential at B. So now we have an expression for the potential difference between 2 far points in terms of an integral. So this is called a path integral. This expression, when you write down integration of e dot dr, which is this limit of sums, it's called a path integral. A path integral, as I said, you have 2 points, you define some path. And you know the electric field at every point on the path. And you cut up the path into an infinite number of parts. Here in this part, I just made it 5 parts, but of course you should make them infinite number of parts. So that's what this integral is. You have to get the dot product for this part, 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 and for this part. And for the infinite number of parts, it should be an infinite number of parts. Each one of those dot products is a number. You add all those numbers up, you get this integration. So you saw that the result doesn't depend on the path we take. If you took a different path, you will be cutting up that path into an infinite number of parts. When you add the potential differences along that path, you'll get the same result. You'll get the potential at the beginning minus the potential at the end. So whichever path you choose, it doesn't make a difference. VA minus VB will always have the same value. And so the conclusion of this part is the definition, the original definition we gave for the relationship between electric field and potential was the differential form. Ex is minus partial V by partial X. Ey is minus partial V by partial Y. Ez is minus partial V by partial Z. Now the inverse expression of this, if you want to get the potential difference between 2 points, you integrate E dot dr. So these two expressions are just the inverse of each other. So again, to summarize, these are the two basic definitions or ways of expressing the relationship between the electric field and the potential. We started with this one and we showed that this one is correct. Some textbooks start with this definition and then they show that this one is correct. It doesn't matter really which way you start, but they're both equivalent. They're just, one is a differential form, one is the integral form. And we showed also that the potential difference between 2 points doesn't depend on the path.